Electric fields. This is where we're drawing some diagrams. Guys. Okay. So, electric fields are the area around something or region of space in which charge experiences a force. Okay. So anything that's charged has an electric field around it. Depending on what it is, guys, have different types of fields, okay, and different shapes of fields even. Okay. So electric fields exist around charged particles, charged metal plates, and between charged parallel plates. We cannot see electric fields, so we represent them by electric field lines. So quite similar to sort of like when you did your magnetic field back in second year, and you sprinkled your iron filings on, but you can't see it, they're invisible to the naked eye. So there are some rules for electric fields. The arrows on the field line show the direction of the force experienced by a positive charge placed at that point in an electric field. So you're basically imagining you bringing in a positive charge, you hold it, and then you let go of it. Where would it go? Okay. Electric field lines always start and finish on electric charges, and the stronger the electric fields, the closest together the field lines. Okay. So let's think about that positive charge. Okay. So we're bringing a positive charge. There's a positive charge there. We've got one in our hand. We bring it here, and then we suddenly let go of it. It will be repelled away from this positive charge, wouldn't it? Because light charge repels. And that's why the field line goes down like that. Bring it here, repelled away from it there. Okay. So that's a way to think about when you're thinking about field lines and the shapes of field lines. So if you're bringing a positive charge here, next to the negative charge, which direction will it go? Towards the negative. Okay. So the negative one looks like the positive one, but the arrow is in the opposite direction. So we'll draw that one in first. I'm sure you guys can draw this a little bit neater than I can. Okay. Incidentally, the ones around the one positive charge or one negative charge, they're called radial fields because they sort of radiate out. This part C is a little bit like your magnetic field lines. Okay, so again, you're thinking about positive charges. You put a positive charge here and you let go of it and go that direction towards negative, away from the positive. So we'd start off with a line like that. Obviously, it would go away from the positive charges. It would go towards the negative. And you'd also have something like that. And if you're ever taught by me in second year, we call it the sort of burger shape. You've got like a burger bun and letters sticking out the edges of it. So similar to the magnetic field lines. And again, positive and positive, this one here, similar to your magnetic field lines again, you'd have them going away from your positive charges, but they don't want to go towards the other positive charge, so they kind of like repel away. And you get this area in between it where there's no field. Remember when you had a north and north pole and north pole if you had magnets? Doesn't matter how close they get. As long as they don't cross over. Yeah, that's fine. This one, we've got a negative plate. So this is just a long, thin negative thing and a positive point charge. So it would go away from the positive charge and towards the negative plate. So we'd obviously get a line like that. Then we'd get some lines like that. And at the other side, we'd just have it firing away from the positive. No, as long as you've got the general shape. And F, you could probably guess, just lots of straight lines. Ideally, they would be equally spaced and away from the positive towards the negative. And that last one we call a uniform electric field because they're sort of equally spaced. And that's the kind of, we'll probably come across that the most in this booklet, the uniform electric field. I'll leave that for a little bit. I think some people are still drawing. By all means, have a read through pages 4 to 6 while we're waiting, but I'm going to get you to read through that a bit later. I'm going to go through a little bit more theory because you can read, I'm sure, in your own time. Has everyone drawn those? Anyone still drawing? Oh, okay. Right, so as I said, we're just going to skip past these. I'll get you guys to come back and have a read through these yourselves rather than me reading it at you. But I want to skip to page 7, where you can see one of those uniform fields again. Okay, but instead of like that, they're like that. Okay. So what we have is we've got these two parallel plates. This is positive, that's negative. So the field lines go remember positive point charge, bring in and let go. Field lines away from the positive and towards the negative. Okay. So we've got a small positive charge plus Q and a small negative charge minus Q placed in a uniform electric field. Okay. So it says on the diagram draw force vectors, so an arrow, to represent the electrostatic force applied to each charge by the field. So, what do we think? Which direction? Point in the direction that you think the positive charge is going. Towards the negative, gets attracted towards the negative. And what about the negative charge? Yeah, gets attracted towards the positive. Okay. So that's basically what I want you to draw in, just a little arrow. Showing in which direction they would move. Now, here is a question. Do they move at a constant speed or with a constant acceleration? And it says justify your answer. Anyone want to have a stab at it? Okay, are they experiencing a force? Yeah. Is it an unbalanced force? It's getting... So, at this point here, in the middle, it might be a balanced force, but at this point here, it's a much bigger force from this, from the opposite. So we've got an unbalanced force. Yes. So if you've got an unbalanced force, F equals ma, we have an acceleration. Okay. So they experience unbalanced forces. Therefore, constant acceleration unless of course they end up with another force applied to them and it could balance the forces out again. But yeah, if they were right in the middle, then they could potentially have balanced force. But if they're anywhere but the middle, they'll have a bigger force from one side than the other. Okay? And we'll find later on that we can sometimes treat these a little bit like projectiles because they've got an acceleration. Right, so equation that you have come across, I think, in third year, potential difference, work done, and charge. But you didn't really talk about what it meant, really. You just were given an equation. So, the simple potential difference is V, or voltage. The SI unit is the volts. So, the definition of voltage that you need to know is the potential difference between 2 points in an electric field is the work done, or the energy done, energy provided in moving 1 coulomb of charge between the 2 points. Okay, so that's really what that equation means. You probably saw it written down as W equals QV. Okay, but that's written down that way just because it's giving you a definition. So it's the work done moving 1 coulomb of charge between 2 points. So as I said, you probably see it written, and you probably will see it more written like that, W equals QV. Okay, where V is your potential difference, PD, or voltage, in volts. W is the work done in joules because it's energy, and Q is your charge in coulombs. And if 1 joule of energy is needed to move a charge of 1 coulomb between 2 points, then the potential difference between the points is 1 joule per coulomb or 1 volt. Okay, so there's nothing really new there that you haven't come across before. It's just a different definition of voltage that you might have seen before. Okay. And just to put it into a little bit more context, work done and potential energy. So we're going to compare the electricity with like your mechanical potential energy, so lifting something up. So in the diagram below, there is a misprint that should be a positive charge there. So that should be positive. In the diagram below, work must be done to move the charge plus Q towards the positive plate through a potential difference V. So you have to put in work to move that. That does not want to go that direction, does it? So if you want to move it, you have to put in a certain amount of work to make it go from the negative to the positive. You have to pull it. Okay? And that amount of work done is given by, in a normal mechanics, if you were pulling something, the work done would be force times distance, wouldn't it? But in an electric field, the work done is the charge times by the voltage. So the size of the charge times by the voltage between those 2 plates. Okay? So when work is done, moving the charge through the electric field, the work done is stored as electric potential energy. Okay. Whereas we've encountered this concept before if you lift something up. Okay? So if you lift anything up, a rock or a pen, you lift it up, yeah? You're doing work to lift it up, force times distance, and it's stored, when it's up there, it's stored as gravitational potential energy, okay? So it's that potential energy. We haven't really talked about electrical potential energy before, we've just called it electrical energy, but it's still got that potential. If you look here, you're moving this along here, you're holding it there. Okay, it's got that electrical potential energy, it's got the potential to move back. Just like if I've moved this up and I'm holding it there, it's got the potential to drop as soon as I let go of it, hasn't it? It's the same kind of physics, but slightly different equations. Okay, so we've encountered this concept before. When a mass is lifted in a gravitational field, the work done lifting the mass is stored as gravitational potential energy. And just a question at the end, before I get you to do some questions yourself. If the mass is then released, what happens to the gravitational potential energy? Changes into kinetic energy. Yeah. So changes into EK. So what happens, do you think, when I let go of the charge? Changes into kinetic energy. Yeah. So the work done is equal to the work done lifting it, or the work done moving a charge across, is equal to the kinetic energy gained. Okay. So we'll talk more about that kinetic energy stuff later. But what I'd like you to do is I'd like to do some questions based on just what we've done today. So page 1 of your new question booklets is on electric fields and then using that equation W equals QB. I don't think it'll take you very long. If you finish that, then go back and read through the uses of electrostatics. I'll write that on the board.